All right, welcome back. We're going to do the second part of Lab 1, which is looking actually at simulations of these scaled sequences. We had just finished wrapping up, here I'll pop it back up. We just finished wrapping up here the first lab here on the law of iterated logarithm. And we were talking about different ways to scale Sn, right? Different ways to scale the sum of the observations and get slightly different behavior. So there's a file in the Dropbox called Lab1 Examples, and it's code and output so you can see what's going on. And it's an old school Sweeve, might even be a Sweeve document. And it's got everything here. And I'm not actually going to go line by line through the code, but I am going to talk about what was done. And so in this case, the data that we're using, the x's here are from a normal 0, 1 distribution. And here, for example, the scale is 1 over 1. So you can see, so I'm just multiplying by 1. So basically, I'm looking at this, which is Sn. And I want to know, where does this converge to? Well, here you have to be a little careful about what you mean by converge, because the expected value of Sn, right? The expected value of Sn is going to be n times 0, right? So that's going to be 0, right? But the variance of Sn is going to be n times sigma squared. And so the limiting, in some sense, the limiting distribution, I want to write it as 0 n sigma squared, but I know that I'm not allowed to have n here in the limit, right? You can't have n in the limit when this is letting n go, whoops, let's see, so I wrote that wrong. So this is letting n go to infinity, which means we would write it as this, as n goes to infinity. So I can't have n here. So effectively, it's a normal distribution with an infinite variance, and that's not a distribution anymore. So I put this out here just so that we can see a little bit about what we're going on. So if I don't scale, I get this statistic xn. We're going to simulate paths of this to see what happens. And here's the variance. And if I divide by 1 over n, of course, this is just the plain old sample mean, right? And its variance is sigma squared over n. Right? And if I divide by 1 over the square root of n, then the variance is just the plain old sigma squared. And if I divide by 1 over the square root of 2n log n, I've added that square root of 2 there from the law of the iterated logarithm, which was the limit, then its variance is going to be sigma squared over something. And notice it's sigma squared over 2 log n. So this variance is getting smaller, but very, very, very slowly. So this is some code for putting these things together. I'm going to pick a different color here so it doesn't contrast with what's on the plot. And basically, it's pretty simple. I generate some data, right? Generate a long vector of data. Then I take the cumulative sum of that vector. I scale it, and I plot it. And I do that over and over and over and over and over again to see what I'm doing. It's not very hard to do at all. And here are some examples. And now I'm not going to be able to get all 4 on the screen exactly. So let's just pay attention to the first 2. So this is what the sequence here looks like, okay, when it's not scaled. These are just sums of random normal variables up to a sample size of 500. And you can see that this distribution is just growing. The concentration, there does appear to be maybe a little bit of extra concentration around here. That's what this histogram sort of shows. It's sort of a smooth histogram at the end. But in reality, what will happen is this will have some weird behavior out in the tails. And because the tails are not well defined here, right, because this can go on forever, so it's always going to look like the tails are a little bit less thick. But at infinity, everything's very basically flat all the way across. Now, if I take this sequence here, and I'll tell you what this blue and red line are in a second. If I take this sequence here and divide by 1 over n, I get something very different. So rather than exploding out, I get this convergence inward. Okay, and so these bounds, one is a Chebyshev's bound, and one is just, I think, like a 99% confidence interval. I'd have to go. I'm just forgetting at the second what this is, but there's some bounds on the sequence to sort of show you what's going on. And here you can see that okay, everything's basically going right to 0, right? Now, of course, this isn't infinity. You've got infinities a long way off here. So this will even squish down into a point as you go on. But the behavior is very different, right? Here, don't forget the variance is n sigma squared. And here the variance is sigma squared over n. And so we see different behavior. Now let's take a look at some of these other things go on. Now if I divide by the square root of n, do you remember what our variance was? It was Sn over the square root of n. Right? And if I take the variance of that thing, the variance of the top, so if I take the variance of that guy, I'm going to get n sigma squared, because it's the variance of n independent random variables, over root n squared, so it's just going to be sigma squared, so it's going to be constant. And so look at that. So that's my sequence. If I scale it by root n, I get that looking sequence. And in fact here, these are the Chebyshev bounds, remember, and these are like the 99, there might even be 95% confidence intervals for the confidence regions for the sequence. What's interesting here is you have a pretty ugly looking curve, but the central limit theorem says, oh, hey, that curve by the central limit theorem says, oh, yeah, that's going to be normal 0, 1, right? And that's just because Sn over root n is equal to root n times x bar, and we can also write, right, as mean 0, variance 1, and so that's going to go to normal 0, 1 by the central limit theorem. So what the central limit theorem is really describing here is the shape of this distribution at infinity. Well, so we don't have infinity here, we have 500. It turns out that that's pretty close to what we're going to see for a normal distribution, standard normal distribution. 500 observations, a lot of observations, but that's basically, this will smooth out eventually to look exactly like a normal distribution. The more data you have, the more normal that thing will end up looking like. And you get this nice behavior where everything sort of looks flat. And so very interestingly, we went from big here, right? I mean, we were extending out here to coming together to a point here, and now we're even here. So I say, okay. So what's in the middle, right? I mean, so the law of the iterated logarithm is supposed to be in the middle of this top right one and this right here. And that's because I'm adding a little bit to the denominator. So I have my square root n here, and then I'm adding a little bit more, I'm making the denominator a little bit larger. And so what you can see in this case, okay, you can see that this is just slightly, the variance is just slightly less here for this case than this case. Because here the variance is sigma squared over 2 log n. That's the variance. Because that n, this n here, cancels with that n there. All right? And you can see there is some narrowing here. There is some narrowing, but it's very, very slow. And if I went at way far out, what you would see is that these do eventually narrow, but they narrow so slowly that every now and then something's going to pop out or be far away. Right? So that supremum is out there. Okay? All right. So you can, this is a nice way to picture what's going on. So let's do something else and scale it even more. I mean, to sort of illustrate the law of the iterated logarithm, what happens if I make this bigger or smaller. And by this, I'm talking about this here. Right? I'm making the denominator bigger as I go down the table. It starts off with a little bit less. That's less than the law of the iterated logarithm, right? Because here this is actually growing because n to the 0.1 is here. And here I'm getting smaller. So just added a little bit of epsilon. Let's take a look at what we've got going on here. We've got some interesting things here. Now, if I reduce that rate, okay, that's this first thing, right? Because I made it smaller because the law of the iterated logarithm has n to the 1. Notice what you're seeing. This is just slightly getting bigger. And in fact, that's what happens. You're just going to slightly get bigger. So your maximum now is never going to be contained, right? Because you're getting bigger as the sample size gets bigger. This grows, and so every now and then you're going to be far enough away from here that you're not going to be able to converge almost surely. You can converge in probability because there's enough mass here, but you can't converge almost surely because you get these extreme sequences that are far enough away. Here now, if I give a little bit extra, so if I make that scaling constant even bigger in the denominator, you can see it's narrower here. So we've really started to pinch in here. And here we go, here's 1.5, and here's basically squared. So it really pinches it in very quick. So you get a good sense of what playing with the rate does. Now let's look at something fun. Let's change it up because the normal distribution is a nice, clean, easy to look at distribution. So let's try it now with the Cauchy. And what do we know about the Cauchy? Well, for the Cauchy, right, there's no mean. It doesn't exist. The tails are too heavy. Right? So there is no convergence. So what does x bar converge to for the Cauchy? Nothing. So what does a picture of nothing look like? Right? I mean, if I want to draw what this looks like, and I want to draw these sample means, you'll have sequences that actually will look like they're drifting to 0, and then all of a sudden they'll drift away, and then they'll start to drift back, and then they'll do this. So they actually have some tendency, a little bit of tendency every now and then to get towards 0, and then they jump. They have these weird jumps because you get an observation that's so far out in the tail that it pulls the whole mean away. And they never get close enough to settle down, right? And so that's what it means when you say the mean doesn't exist. So I don't know if you've ever seen these pictures before. The Dropbox, in the readings part of the Lab 1, there are some PDFs there from another class where I give some examples of what happened in the Cauchy distribution. They're worth reading. They're a quick read. And they're just some class notes. So let's take a look at what these pictures look like. And look at that. So here is the sample. Here's just the regular sums. Now you got to pay attention to the scale. That's 10,000. That's 100. Here's the mean. And here's exactly that behavior that I showed you. Something up, pops up, and then comes back down. Pops up, comes back down. Pops up, comes back down. Right, so things are kind of getting close, but wherever you are, there will be this popping and leaving distribution. So there's no convergence in the mean because at any point you could just drop. I mean, that's like, for instance, that's a big drop, right? You've got 250 observations and your mean just shifted by 80. So you saw a huge negative observation. Just pulled that away. Okay, so this is why the law of large numbers does not work. Doesn't work. No. Okay. Similarly here, since the law of large numbers doesn't work, you're not going to get a central limit theorem type behavior. Here too, this is way more dispersed than a normal distribution would look like, and you can see it's way spread out. And when you do the iterated logarithm here, you've got the same problem with these large dropouts and coming together. So this is an example for the Cauchy when we talk about the mean not existing, what we mean. There's still some tendency for a smaller set of these sequences to behave like we think they're going to be. But at any point in time, any one of those sequences can just drop out of a neighborhood of the truth and just go away completely. And it might come drift back again, and then eventually you'll get another large or small, extremely small observation will pull that mean away. So it can never settle down near the truth. The nice thing, the one thing we know about the Cauchy is that's not all terrible, because if I can't learn about the mean, because it doesn't exist, I can learn about the median. So let's take a look here at scaling the median and what happens. All right, so I'm just going to take the median, the scaled median, this reduced scaled median here, and then this median scaled by the law of the iterated logarithm, just to sort of complete the picture. Here you can see, oh, I'm taking the median, but some, this is just the raw median. It's growing over time because you've got very heavy tails, right? And so the distribution of the median is going to grow over time because you're just going to keep picking up those way, way, way far out observations, and that will pull the median, in a particular direction. Now, if I scale the median by 1 over n, it's looking like I have some nice behavior here, right? I have some convergence to 0, which is, in fact, the actual median in this case. And you can show that this is true, actually, right? That this happens, that the median is consistent. Here's 1 over the square root of n. And again, for the median, we're getting similar behavior like we saw before, right? A constant group, and so then there's some recognizable behavior there. It's complicated to identify what that is, but you can do it. And then if I just increase this just by log n, just a little bit more, I get a little thinning out here as this comes together here. More than here. So if I were to take these through, I'd be up here. So these are a little narrower. And so this is how it works. So I would encourage everybody to take the time to either put together these simulations themselves or get comfortable thinking about these things and talk about them. And because what we're going to do in class is we're going to end up, when we do Taylor series expansions or we want to know behaviors of likelihood functions, they're going to be sums of lots of likelihoods. We're going to have to scale them. So we might, if we want them to converge to some constant, we might scale them by 1 over n. If we converge to a distribution, we'll scale by 1 over root n. And the scaling factors are important. And so this is your one way to begin thinking about these things, because they're an important tool. All right, so be sure to talk about this, raise any questions you have in lab, or raise them in class, and I'd be happy to talk about them. Thank you.